In this video, we'll study differentiation of measures. You will have already studied similar ideas in measure theory when you learned about Radon-Nikodym derivatives, but here we'll strengthen these results in the case of Euclidean measures. As a motivating example to what we're about to discuss, let's review some basic calculus and recall what a derivative is. So the derivative of a function is a value that describes the infinitesimal behavior of a function at a point x, in the sense that it's defined using information only about points as they approach x, or only using values near x. If the derivative is 2, then that means that as we zoom in on the graph of a function over that point, the function begins to look like a line of slope 2, and the number 2 is telling us how fast the function is increasing at that point. The fundamental theorem of calculus gives us a way of relating this small scale or fine information about a function, i.e. the derivative, back to the function itself. So for example, if the derivative is bounded by some number m at every point, then we can explicitly bound the differences of the original function f. There's a similar phenomenon with measures, whereby the infinitesimal behavior of a measure dictates its global behavior. We'll quantify this infinitesimal behavior by defining analogous derivatives of measures. So let mu and nu be locally finite Borel measures. We define the upper derivative of mu with respect to nu at a point x to be the lim sup of the ratios of the mu and nu measures of the ball centered at x of radius r as r goes to 0. We similarly define the lower derivative by taking lim imps of the same ratio. Finally, the derivative of the measures is the value we get if the lower and upper densities equal each other. So note that this limit may not exist at some points. As we will see often in this class, just because we slap some functions together doesn't mean, just because we slap a function together doesn't mean that it's Borel measurable. So there's this constant chore in geometric measure theory of having to verify Borel measurability whenever we define a new function. In this case, the functions we have defined are Borel measurable, and we leave the details as an exercise. Just as the fundamental theorem of calculus turned bounds on derivatives into bounds on the original function, bounds on derivatives of measures result in bounds between measures. So given a positive and finite number t, if the lower derivative is at most t on some set A, then the mu measure of A is at most t times the nu measure of A. Similarly, if the upper derivative is at least t, then the mu measure of A is at least t times the nu measure of A. So it's easy to check that the first statement implies the second. So we'll just prove the first part, since it's a good example in how to use the Radon property for measures and the Vitali covering theorem. The idea of the proof is as follows. So because the lower derivative of mu with respect to nu at each point x in A is at most t, that means that for every x in A, we can find a ball centered at x for which the ratio of the mu and nu measures of that ball is at most t. So in other words, the mu measure of the ball is at most t times the nu measure of that ball, approximately. Okay, so if these balls approximate the set A well enough and they don't overlap too much, and they also approximate the nu measure of A simultaneously, then that gives us a way of relating the mu measure of A to the nu measure of the set A. So let's put this into mathematical terms. So I'm going to let epsilon be bigger than 0. This will be some number I send to 0 later. So the assumption that mu nu x is less than or equal to t for all x in A. All right, so this implies that for all x in A, we may find a radius r bigger than 0. So if we set b of x equal to the ball centered at x of radius rx, then the mu measure over the nu measure of this ball is less than t plus epsilon. So that's because the lim inf of the mu measure of a ball over the nu measure of the ball as the radius goes to 0, the lim inf of that is at most t. So that means that for sufficiently small radii, this has to be less than t plus epsilon for any epsilon that we specify. Okay, so Vitali's theorem implies that there exists a subcollection, Bi, of disjoint balls, disjoint closed balls, such that they cover almost all of the set A. So thus, this implies that if we look at the mu measure of A, okay, the balls cover almost all of A, so this is at most the union, or the mu measure of the union of these balls. By subadditivity, this is at most the sum of the measures of these balls. Now, by our assumption about the ratios of the balls, so remember these Bi's are each equal to some Bx for some x satisfying this inequality, this is less than t plus epsilon times the sum of the new measure of the balls. Now, because they're disjoint, we can pull this sum together. So this is equal to t plus epsilon times the new measure of the union of the Bi's. Okay, so now we're at a bit of an impasse, because remember our goal was to approximate the set A by a union of disjoint balls where we had good control on what their ratios were with respect to the corresponding new measure of the ball. And so we wanted to use that to give us a comparison that would result in a bound on the mu measure of A in terms of the new measure of A. But now we don't have the new measure of A over here. We have the new measure of a slightly larger set, or a set that properly contains A. Okay, so the problem with this, so the way that we resolve this is really what we should have done at the beginning is used the Radon property. So when we said let epsilon be bigger than 0 here, we should also say let U contain A open such that the new measure of nu without A is less than epsilon. Okay? And again, this follows because nu is a Radon measure. So there exists this open set, and then now we also pick these radii Rx bigger than 0 so that, yes, this ratio holds, and the Bx are contained inside this open set U. Okay? So now, what that tells us is that this union of the Bi's is contained in the open set U. So this is at most t plus epsilon nu of this open set. Okay? And recall that this open set is approximating A, or that is to say, the difference between the new measure of U and A is at most epsilon. So this is less than t plus epsilon nu of A plus epsilon. Okay, so now letting epsilon go to 0, we get nu of A is at most t nu of A. And that's the proof. So I did it in the slightly awkward style of purposefully leaving out this step about the open set, just to kind of emphasize why the Radon property is important and how what is the kind of place that we need it in a typical argument. So here it was useful because basically when we did this covering of the set A, there was this excess. Like we were trying to approximate the set A, but we could only approximate by a union of balls that properly contained it. So we can use the Radon property and ensure that the balls are, we can use the Radon property to find this open set very close in measure to the set A. And then by choosing our balls to be within this open set, we can control the excess. We can say that the excess is no more than epsilon times the measure of A. So the previous lemma is a first step towards us being able to characterize absolute continuity in terms of these derivatives. So recall that a measure mu is absolutely continuous with respect to a measure nu if the null sets for nu are also null sets for mu. Two measures are said to be singular if we can find a set A for which the restrictions of mu to A and nu to A complement are 0. So, for example, any two measures with disjoint supports are automatically singular. The converse, however, is not true. If we have a measure that's a linear combination of Dirac masses at the rationals, for example, then this is singular with respect to Lebesgue measure, since the rationals have measure 0, whereas the measure mu is 0 on the complement of this set. However, the supports of these two measures are the same, since the closure of the rationals is equal to the whole real line. Finally, we see that Lebesgue measure is absolutely continuous with respect to counting measure, almost trivially, since the counting measure of a set is 0, almost. We now have the following version of the Radon-Nikodym theorem. Given two measures, mu and nu, two Radon measures, the following hold. First of all, the derivative exists nu almost everywhere. That is, the upper and lower derivatives exist and agree nu almost everywhere. Next, for any Borel set B, we have the integral of the derivative over B is at most the integral of the derivative over B with respect to nu is at most the mu measure of B, and we have equality if if mu is absolutely continuous with respect to nu. Finally, absolute continuity is equivalent to the lower density existing mu almost everywhere. So this gives a characterization of absolute continuity in terms of lower derivatives. So a few comments are in order. So first of all, you might be thinking, wait, if the derivative exists almost everywhere, as in item 1, wouldn't that imply the lower densities exist, and hence mu is absolutely continuous with respect to nu always? Well, the difference is that this derivative exists nu almost everywhere. So the density existing mu almost everywhere is a harder condition to satisfy. So that's why one does not imply absolute continuity. Another thought you might have is that earlier I said Lebesgue measure was absolutely continuous with respect to counting measure, but clearly equality in item 2, or the equality in item 2 can't hold in that case. And it definitely doesn't, but remember that counting measure on the real line is not a Radon measure because it's not locally finite, and this theorem only applies to Radon measures. Finally, if two measures are singular, but one says the derivative exists nu almost everywhere, well, what is the derivative then? Well, you can show that in this case it must be 0, and I'll leave that as an exercise. So I won't prove this theorem here, but I'll just say that the heavy lifting has mostly been done in the previous lemma that we discussed earlier. In fact, that lemma is used in proving each one of these items. So if you look in notes or in Mathes's book, you can check the proof for yourself. So finally, we have the following Lebesgue decomposition theorem for Radon measures. So it says, given any pair of Radon measures mu and nu, we can decompose mu into a measure that is absolutely continuous with respect to nu, given by some function f times nu, plus a singular measure lambda. So as I say, a measure that's singular with respect to mu. And the proof is easy given the previous theorem. So by the previous theorem, the place where mu is absolutely continuous with respect to nu is the place where the lower derivative is finite. So the restriction to this set is our absolutely continuous part of mu. And the function f is just equal to the derivative of mu with restricted a with respect to nu. And then the singular part is just the measure mu restricted to the complement of this set. We end this lecture with a corollary of the previous results that will be very important for us later on in the course. So it's a Lebesgue density theorem for Radon measures. So the first part of it says that if we have a Radon measure nu, and we have a locally integrable function f with respect to nu, then the limit of these averages as r goes to 0 converges to f of x for nu almost every x. So the way this follows from previous results is as follows. So first of all, notice that if we set mu equal to fd nu, or just f times the measure nu, okay, then this is absolutely continuous with respect to nu. So the previous results imply that if we let d be the density of mu with respect to nu, then the nu integral of the density for any Borel set is equal to mu of the Borel set by the previous theorem. But by definition of what mu is, this is the same thing as the integral of f with respect to nu over this Borel set. Now, In particular, this holds for all balls B, not just Borel sets. And it's not too difficult to show that if you have two functions d and f whose integrals agree on every ball in Euclidean space, then this implies that d equals f nu almost everywhere. Okay. So thus what that implies is that if we look at this average right here, okay, what is this? So we're taking an average, which means we're dividing by the mu measure of this ball. But when we integrate f d nu on this ball, what's on top is the mu measure. And as r goes to 0, this goes to the density, which we have just shown is f, which is that value there. And that's how you prove the first part of the theorem. Then the second part of the theorem, you just get by letting f equal the characteristic function of some set A. And then you get the following, that given a new measurable set A, then if you look at the density of A inside a ball center x of radius r, so that's what we call this ratio, then as r goes to 0, this ratio will converge to 1 for nu almost every point x in A, and this ratio will go to 0 for nu almost every point not in the set A.